And then if you look down here, the sulfite is going to be the lesser one. It's the one with less oxygens. It'll also be less common. Okay. And again, an easy mnemonic to remember that is you ate the meal versus you took a bite. Ate the meal is more, taking a bite is less. Okay.
Like the mnemonic.
Yeah, it works nicely.
Mm-hmm.
Yeah. This right here is typically called hydrogen sulfate. This would be bisulfate. If you ever see a bi, or if you're thinking of bi, it has a hydrogen attached. And the reason it's called bi is because you have dissected the charge. Okay? They happen in things like carbonate and sulfate, where you have a 2- charge. You put a hydrogen in, and you go to a 1- charge. So bi, dissect charge. Okay? Bicarbonate is the one you probably have heard of or seen before. That one is the one that's actually baking soda, in case you're wondering. Okay, anyways, this right here is going to be the phosphate. Anybody know of phosphate before? Everybody have heard of DNA? Okay. It has a phosphate backbone, and that's the phosphate. Okay. So those would be attached to sugars and alternate between sugars. And that's your phosphate backbone. I know, it's wonderful. Anybody ever heard of ATP? That's triphosphate. Guess how many phosphates it has? 3. ADP. 2 phosphates. That's di. MP. 1 mono. Yep. Okay, this one's manganese, by the way. It's permanganate. And this is sometimes used to care for wounds. It's usually a purplish color. So if you've ever seen like a purplish color they spread over a wound, that's probably this. The other thing it could have been is iodine, though iodine is less often purple. Okay.
Very orange.
Yeah. Usually very kind of depends on the concentration, but if you're using medical grade, it's going to be an orange color. Yeah. I will ask like 1, maybe 2 questions that are going to be like reading level questions of, hey, did you read through all the parts? But realistically speaking, you can't actually fail an exam off of 1 or 2 questions. So, like if it's between memorizing the names for these things and knowing what the polyatomic ions are and their, use, more efficient a time would be this. Yeah. Okay, now let's talk about naming ions. So for metal ions, we're going to add the word ion to the name of the metal. I know it is super complex, isn't it? So sodium is going to become sodium ion. Iron is going to become iron ion. If you have aluminum, it's going to become aluminum ion. Yeah, I know. Chemist, right? Okay. Now, iron is a little bit more complex because iron can have multiple different charges, right? Everything that's in the transition metals in the middle there, they can all have multiple different charges. And so you actually have to list what the charge is going to be. Okay? For example, iron commonly happens in charge 2 plus and charge 3 plus. And so when you name iron, you need to name it iron 2 ion, iron 3 ion. Now, it's going to use Roman numerals to name these. Does everybody remember your Roman numerals? Anybody not remember your Roman numerals? Okay. How do you do 4 again? IV. How do you do 5? V, 6, VI. Very good. Okay. Always got to double check because sometimes, right? Things happen. All right. So for nonmetals, you're going to add the suffix "ide" to the end. And so you're going to exchange the end of the nonmetal to "ide." This is going to replace those last few letters of the name of the element. How exactly it replaces? Well, so you can say it. Okay? That's actually how they did that. It's so you can say it, so the vowel is in the proper place to say it. So, for example, normally we would have fluorine, which is F on the periodic table. As an ion, F minus, it's going to be fluoride. Okay? Anybody ever heard of fluoride toothpaste?
Mhm.
Yeah. Or fluoride in the water? You know, that mind control thing the government does? Everybody knew that's the conspiracy theory, right? Okay. The science for that's actually super shaky for them adding fluoride into the water. It's actually like really, really, really shaky science. It's more like a totem for hoping for good teeth. It's science. But maybe it works, maybe it doesn't. I don't know. Most polyatomic ions end in 8. The ending "ite" is going to be used again for one fewer oxygen atoms. Some of the exceptions to these things, of course, all these things have a little bit of exception, is hydroxide. This is OH minus. Hydronium, which is H3O plus. And cyanide, which is Cn minus. These are going to be exceptions to these rules. And they're mostly based on historic things. Okay, these right here, some cations and anions. They're very common to see. So they're common uses where you find them. Has everybody heard of sodium chloride before? It's table salt, isn't it? Dun dun dun. Okay, and so you actually kind of already knew these naming rules because you've heard it before. Many, many, many different places, right? Because you've lived your entire life surrounded by science and chemistry. It has created the entire world that you exist in right now. Okay? Does anybody know what would happen if we actually got rid of all the chemistry right now? We would have to kill about 7 billion people. Okay? Without the chemistry, we couldn't support 8 billion people on the planet. Right? That actually, just fertilizers alone accounts for about 2 billion of that. So if we actually were to ban fertilizers, we would have to get rid of at least a third of the population. As evidenced by the countries that ban fertilizers. And mass starvations within 1 to 2 years. So, anyways, maybe you could come up with a new technique in the future, but you can't just ban the thing and have no replacement. Okay, now, when a metal and non-metal combine, what's going to happen is the metal does not hold on to its electrons very well. Okay, the electrons tend to escape the metals. The non-metals, on the other hand, hold on to electrons much better. Okay, much more strongly. And so when they come together, your metal is going to lose an electron to the non-metal. And you're going to form ions. So in this case, we have sodium metal and chloride, right? And chlorine, actually, in this case. This is going to have the sodium losing its electron to the chlorine. When you lose an electron, you're going to be more positive. So you'll have a positive charge. When you gain an electron, you're going to be more negative. So you're going to have a negative charge, right? If you lost 2 electrons, what would happen?
Twice as positive. Twice, but
No, you're exactly right, yeah. You'd be 2 plus, right? 2 positive charges. Right now, we're a 1 positive charge. And so this right here is then what's referred to as ionic bond. Once this is positive and this is negative, what's going to happen to those? What's attracted together? Is positive and negative attracted together? This, isn't it? And so once one becomes positive, one becomes negative, they're going to be attracted, and they're going to pull each other towards each other. Okay? And that's called ionic bonding. That's all that is. All right? Now, your typical ionic bonding does not actually look just like this. You will not have just a single pair. Okay? Like if you're looking at a salt crystal, what you're actually seeing is billions of these all clustered together. Okay? Just one after another. You'll have a positive, negative, over and over and over. And then down here, you'd have a negative, positive, over and over and over, and so on. Anybody ever grown a salt crystal? Or seen like the big salt crystals you sometimes give horses to lick? Okay. That's what that is. That's growing salt crystals. You're just adding more positive negatives in that repeating pattern. And that's why this crystal just sort of gets bigger and bigger with repeating patterns of the same crystal, right? And it looks like a fractal or something, doesn't it? Yeah, because it kind of is. So, fun stuff. When we have ionic bonds, we get a resulting ionic compound. So that's a compound that is ionic. How can I tell it's going to be an ionic bond and ionic compounds? So we have
more than one molecule versus a single molecule.
Yep, we have two different atoms, right? And the other part of it is that one of them is going to be a metal, one of them is going to be a non-metal. Okay? So we have a metal and a non-metal. They come together. The metal loses electrons, the non-metal gains electrons. Okay. So let's talk about the formula of ionic compounds. The number of ions that combine to form an ionic compound is going to be determined by the charge of the cation and the charge of the anion. So let's say we had a 2+ charge. How many 1- charges do we need to equal that out? 2, right? Yeah. And so whenever you have a compound, if we had a bunch of positive charges, they were all together in one place, what would happen to them? Boom, right? They'd blow up because they'd be repelling each other. So you already kind of knew this by the fact that your table salt doesn't just go poof in your face every time you do it, right? That you don't have all negative and positive charges together, right? It has to be neutral overall. Can you have a little charge imbalance? Yes, that happens. But overall, it's going to be neutral. Okay. Okay. So again, the cation and anions have to combine so as the compound overall is going to be net charge of 0, neutral. Okay. When writing these formulas for the chemical compounds, we represent the number of each particle in the compound with a subscript. Okay. And the charges in the formula of an ionic compound are typically not shown because we typically don't need those charges. We'll know it from the overall formula. Let's do an example. Right. So this right here is just those steps I'd already mentioned. We're going to look at an example here. So I've told you, hey, write out the chemical formula of aluminum oxide. Anybody know what aluminum oxide is, by the way? Anybody have like aluminum cans or aluminum anything? Okay. Have you ever scratched aluminum and it gets really shiny? No? So if you take aluminum and put a scratch in it, what you'll actually see is it gets really shiny. It's not dull like it normally looks, okay? And then it suddenly, over the course of like 10 minutes, will fade and get dull again, okay? And what you're seeing is aluminum metal is actually very shiny. But it's actually pretty reactive. You guys didn't know that, did you? Yeah, aluminum is actually highly reactive to the atmosphere, okay? What happens is it then combines with oxygen from the atmosphere. That gives you aluminum oxide, which is the dull stuff you think of as aluminum. Okay? And the reason aluminum is not normally reacting all over the place and your plane doesn't just like rust and fall down around you is aluminum oxide's very corrosion resistant, very strong. And so it actually protects the aluminum under it. Anybody been on a plane and it says don't bring vials of mercury on it? You didn't notice the sign that says no mercury? Yeah, there's a sign. They're actually checking you for mercury as part of what the things they're checking you for is. If you ever bring a vial of mercury or like a mercury lamp onto a plane and you break that vial of mercury on the plane, it will actually corrode through the plane. Yeah. It takes about half an hour to an hour usually to actually start corroding through the plane, but it does it. And so on one of the flights, it will suddenly just have a hole in it. Because didn't know that, did you? Yeah, pretty interesting, huh? Yeah. Okay, and that's because mercury actually dissolves the aluminum oxide off the surface of aluminum. So, all right. So aluminum wants what charge? We look at our periodic table. So aluminum is 3 steps from the left, right? Can everybody see that? AL. It's under boron. Right. So we look at aluminum on the periodic table, and we see that's 3 steps from the left to being like a noble, right? And so the charge aluminum typically wants is a 3 plus. Okay. It wants to be 3 plus. We look at oxygen, and it is 2 steps from the right. Can everybody say okay? Okay, and so that typically wants a 2 minus charge. Right? And so what's going to happen is the oxygen's going to get a 2 negative charge. The aluminum's going to get a 3 plus charge. Anybody ever cross multiplied? Is that still something that's being taught? Yeah. Okay. We're going to essentially cross multiply here. So to get the same charge for both of these, what we need to do is we need to write this with Al, aluminum. We put the 2 down as a subscript for aluminum. And then we write the oxygen, and we're going to put the 3 plus from the aluminum down on the oxygen. See that we've cross-multiplied how? We have a 6 plus charge and a 6 minus charge now.
So typically when we see a subscript, it means we'd have 2 atoms, 2 molecules of the aluminum, and 3 molecules of the oxygen.
That's exactly what we have.
So that is still the final result?
Yeah, that's the final formula. You got it. Yep. So we have 2 aluminums, we have 3 oxygens, and we know that has to be true for an ionic compound because it gives us an overall charge of 0. There we go.
I don't know if I caught how we got there.
What we're doing is,
but I didn't.
When we put these together, we need to have a net charge of 0. Remember that so far?
Right. We're trying to balance the outer shells.
Yeah, we have to balance the overall charge.
And we're looking at it as on an individual atoms basis.
Yes, right now. What we're doing is we're trying to figure out how to write these formulas out. Because these formulas, when we actually name them, this is just going to be called aluminum oxide, period. That's it. It's going to be the metal, and then oxide for the nonmetal. So, like if you just had this written in a sentence, it would be, I have aluminum oxide. And you're going to have no idea how many aluminums, no idea how many oxygens. Okay? And so how do you figure that out? How can you then write the chemical formula for it from its name? And how you do this is you go up to aluminum on the periodic table, and you know the charge of aluminum and oxygen. Okay? So oxygen is 2 minus, right? Aluminum is 3 plus. Okay. And so at this point, we're here. Is everybody okay to this point? Did I lose anybody there? Okay. Okay. So now how do we figure out what the actual formula for this compound is? Well, we need to have a net charge of 0. Okay? So however they combine together to give a net charge of 0, in this case with the lowest overall number of these possible. Okay? So what we do is we cross multiply them because that's always going to balance out our charge, right? And so in this case, we're going to take the 2 from the oxygen. We need to put it down as the subscript for aluminum because that's like cross multiplying, right? Normally you would have taken like 2x. Well, we don't put 2 in front of it because that would mess up our writing, right? So we put it down here. Does that make more sense?
Yeah, thank you.
No problem.
So do they turn, both of them turn positive?
No, it balances out. So this one's 6 plus altogether. This one right here would be 6 minus altogether.
So it's like they cancel each other out.
Cancel.
They create a neutrality, which is what we're trying to get to.
We are. We're getting to net 0, right? Neutral. Okay? And so they, like, oxygen is still negative. But they're going to balance each other exactly to 0. Is that making more sense?
If they bounce to 0, would it be negative 2? No?
Okay, so remember that oxygen is negative 2 each, right? So if we take that.
I made this sticky and you didn't get a dry erase. Come on, you got one today, right?
I didn't.
You did
Yeah,
it.
yeah. Yeah, I had troubles. So again, remember that this is 2 minus, okay?
Mm-hmm.
Okay. So if we have 3 of those, 3 times 2 minus, that's -6, right? Okay, so the oxygens have -6 charge.
Mm-hmm.
Okay. Aluminum, on the other hand, is 3 plus. And so 3 plus times 2 is again plus 6. So you see, those will actually cancel each other. And that leaves, see up here, it doesn't have anything written. That means it's 0. Okay? When it has nothing written up there, it means it has no charge overall. Right? And so it's actually telling you in the formula itself that, hey, I have no charge.
Are they always going to be able to just simply cross multiply, or will it get?
We'll need one more step. We haven't gotten to that yet. In this case, we don't need to do any more steps because there's not a common denominator. Okay? If we have a common denominator, we need to divide by that common denominator. Okay? So let's say that we had done something like aluminum nitride. Okay? So nitrogen wants how many electrons? We go up to the periodic table. How many steps is nitrogen from a noble?
5.
Nitrogen is N.
Yeah. 1, 2.
So
3, 4.
Oxygen, fluorine,
Oh,
neon.
3.
Mm-hmm.
So how come nitrogen is coming this way, but our aluminum came that way?
Shortest route.
Oh.
Yeah. So the easiest way to remember it is the shortest route. If you want the full answer is metal versus non-metal.
I want the mnemonic. I want the short answer.
So for basically everything you're always going to deal with, it's the shortest route. Okay, because the metals are on the left, the non-metals are all on the top right. Right? But in reality, what it is it's metals lose electrons. Non-metals gain electrons. So the stuff on the top right gains electrons. Stuff down left loses electrons. So that stuff goes to the left. Stuff on the top right goes to the right.
What about our metalloids?
They can have some options, actually. But overall, they tend to lose electrons. But again, that's why they're called metalloids. Is because they kind of do both. They do some things like non-metals, some things like metals. Honestly, you're not going to do a lot of chemistry with silicon unless we start doing medical stuff for like silicon-based life forms or something, which we have not found yet. So be cool. Go full sci-fi. Okay. All right. Did that answer your question?
Yes.
Okay. Fantastic.
Thank you.
No problem. Okay, so again, nitride, nitrogen, it wants to gain how many electrons? 3. So it wants to be a -3 charge, right? Aluminum, on the other hand, wants to lose 3 electrons, right? It wants to be a +3 charge. Okay. And so when you do the cross multiplication, you're probably going to want to write Al3N3, right? Okay. But did you notice that that's the same number, right? Doesn't make sense to multiply both of those by 3. That is not the easiest way to balance the charge system. So if you notice that they can be divided by the same number, you're going to divide them by the same number. Okay? In this case, 3. And so what you'd see is that you really want it to be aluminum N. Just ALN. You don't even have to put a number because that no number means 1, right? There you go. Okay. So again, let's talk about some of the rules for predicting the number and charge in chemical formula. So the formula of an ionic compound, again, is going to have no net charge. All the pluses and minuses have to equal 0. Okay? You have to add up to 0. The charge of the anion is typically what you're going to know on almost every case. It'd be very unusual for you not to know the negative charge because those are all up in the top right and they don't have variable charges. Okay? Very easy to count up. and figure out what the charge is. All right, so the name of an ionic compound, the names of the two ions are going to be combined. You'll put the cation first. You don't actually need to put ion in these cases because you already know it by the second one. Okay? And so, for example, NaCl, this was sodium chloride table salt, right? Notice we didn't put sodium ion, we just put sodium. You know it's ionic because it has chloride after it. Okay?
Are there mnemonics for the ide for chloride and other?
No, they're all ide.
They're all ide.
Yeah. You change the end to ide for all ions.
So all ions end in ide.
Yeah,
period.
all of the elemental ions end in ide. It's only the polyatomics that you have to have a separate ending. Because you have to say that's the polyatomic, right?
Okay.
So, for example, chloride, fluoride, bromide, iodide, nitride, oxide. I pretty much just covered all the important ones. Actually, that took you like 90% of the ones you'll ever see. There you go. Finished. So for transition metals, you have to do one more thing. And that one more thing is you have to indicate the charge on the metal. Okay? So in this case right here, this is going to be copper, Roman numeral 2, oxide. So you put a parentheses with Roman numeral 2, and then oxide. How do you know that that's copper 2 plus? From this formula here.
The Roman numeral.
The Roman numeral tells you, but what if you have to name this instead? How can you know the charge on that copper?
Goodbye.
So what you can do is, what's the charge on the oxygen? Go up to your periodic table, -2. If it's 1-to-1 like it says here, then the charge on the copper has to be +2. Because you don't have overall charge, do you? They have to be equal. It's the position on the periodic table. Yeah. So you look at the periodic table. Everything wants to be, remember that isoelectronic de noble gases? So everything wants to have the same electron arrangement as a noble gas. Okay. And so fluorine is one step from neon, right? And it wants to gain one electron because that will make it the same electron configuration as the noble gas. Fluorine wants to gain one electron to be like argon. Okay. The Ar. Bromine wants to gain one electron to be like Ar, right? Okay. Okay. Oxygen, 2 steps over to be like noble, right? See that? Oxygen, O. Fluorine, neon, right? So -2 wants to gain 2 electrons, which would be -3. Sulfur typically wants to gain 2 electrons, doesn't it? How about nitrogen? -3, right? Wants to go over 3 spots. Okay. Okay. Now, the place where this gets a little different is boron does some interesting stuff, and aluminum is where you start seeing a metal. Okay. So aluminum there is a metal. It wants to lose an electron. And again, we can just count over to the left in these cases because we're not in that middle transition metal. Okay, so aluminum is going to lose 3 electrons to get to like neon. See how you can go left and then wrap around on the periodic table? Yeah. Magnesium wants to lose 2 electrons, right? That making sense? And then you go over to sodium and it wants to do what? So 1 electron lost, right? Yeah. That making more sense?
Yeah, totally.
Okay. So again, make sure you practice because it won't quite fix in everybody's head unless you practice. Okay. So. And if you still have issues, we have lots of chemistry tutors. I have office hours as well. I actually do more office hours than I'm required. I'm actually about 2.5 more office hours a week than is required. And so come in, talk to somebody, get some help. Okay. There is more ways. You may have noticed I have actually explained this in 3 different ways. I can explain it in other ways as well.
The
I
valence
just
electrons is what makes sense, like in my head.
Mhm.
So I'm just filling that outer shell for that octet. Like, okay, I've
Mhm.
got that.
Yep. That's why I do it in this slightly different ways. Because some people it makes more sense for valence electrons. Some hate the valence electrons and just are totally confused by the entire concept of it, and just it makes it worse. And
This
so
is only
spots on the
applicable
periodic
to
table.
main group, though, right?
Yes.
Because the transition metals don't operate this way.
No. No. Transition metals can have variable different numbers of electrons. So transition metals are where you have like we had to talk about copper 2+ here. That's why you have to list that.
Yeah.
Is because you can't actually predict that just from looking at the periodic table. You can kind of get a sense of it, but you won't be right all the time. Okay. And like iron 2 versus 3+. And so what you want to do with transition metals is you want to tell what the stuff it's bonded to is. So like this oxygen here, this tells you how many electrons this copper has.
Is that always like that? Whatever it's bonded to
Yep.
tells me how many electrons it
They will.
has?
Yes, it will. Because they have to total 0 here.
Right.
Yeah.
So if I had nitrogen,
Mhm.
so N, which needs 3,
Mhm.
and I don't even care if it would really bond to.
Let's do iron real quick.
Okay, bind to iron. I don't know where it is on the periodic table.
The iron? Fe.
Okay, I found it. 26.
Yep.
So if I went with nitrogen needing 3,
Mhm.
and I have my iron, does that mean it needs 3 irons? Like I'm just
So
trying to-
you have iron then has a 3+ charge.
How do I know that iron has a 3+ charge?
You would have had this formula. That's why you have these 2 things. So if you have this formula, let's can I borrow that marker again? Sorry.
I'm sorry if
Thank you
everybody
so
else
much.
gets this and I'm
No,
the
you're
only
good.
dumb person here.
No, honestly, if you're asking questions, it probably means somebody else is having them. Okay? But they're maybe too embarrassed to ask. So,
I
it's
want
good
to do
ask.
well in
And
class. So
make
I'll
sure you
follow
do.
everybody.
Honestly, it's not a no,
Okay.
it's good that you're asking. Okay. Okay, so now remember, I'm teaching you the naming
Right.
versus the formula. Okay. So let's say we're given a name for it. It would be iron 2, 3, and then yeah. So if you start with that, that's what you'd be given.
Why am I starting with nitride?
Huh?
Why am I starting with nitride instead of nitrogen? Like, why did I already change the name?
Because that's ion.
Okay.
Again, I'm saying that somebody told you, hey, you have iron nitride.
Oh.
Okay.
Okay.
This is how they would have to write that.
Okay.
Okay. I'm giving you iron nitride
Yeah.
in your directions for lab. This is how that has to be written.
Right.
Okay. And that's because this needs to have the charge here.
Right.
If you don't define the charge, you could have different species.
Got it.
Okay.
Got it.
And so this one right here is going to be Fe.
Yep.
N. Now let's say we did it the other way around. Okay. And I instead gave you the chemical formula. Okay. Now you have to figure out, how do I properly name it? Okay. If I just go iron nitride, and I don't bother putting any Roman numeral here, that could be 2 different forms. I did not properly represent this. I have actually just told you I have some numbers of these and I have no. Okay? That would be the name for this. I have no idea how much of that I have. Whatever. Anybody ever heard of knock, by the way? No? NOx is actually this. It means different numbers of oxygen. And they don't care. That's what that
NOx
actually
is
is.
like
Make fast car go fast.
Yeah, exactly.
Yeah.
Oh, yeah, okay. Like you supercharged your car.
Yeah.
Got it.
Yes.
Oh.
Yeah. So that actually, they're telling you, I don't care how many oxygens I have. It's some number. I don't care. Okay. So this is saying, I don't care how many irons and nitrides I have at some combination. But, and we have the formula here, so we can actually get the correct name. And so we take that nitrogen right there, and we go, what's the charge on the nitrogen? Because we don't know on the iron. It could be several different.
Right.
Okay. And so we go, nitrogen has what charge?
3.
Yeah, 3 minus. And so now, because it's a 1-to-1 ratio, we know that iron, don't we? Okay. And so the iron has to be 3+. And that means this right here has to be 3. That making more sense?
And how would so in either case, how would we need to put it on the test? Because we're not going to write FN and then all the other stuff.
I'd have different options.
Okay.
So I might give you a chemical formula and then A, B, C, D. I'd have iron 2, iron 3.
So it would be multiple choice is what you're telling me so that I could easily see.
Yeah, I do all this stuff in this class for multiple choice. I just don't have time to take 40-something exams plus the other class sections I have and grade them out by hand. Yeah. If I had GTAs, then we'd grade them by hand.
She passed out extra credit. Those could be those people.
You know, I can't. Okay. Legally. Huh. Yeah. Yeah, they actually legally made it. They used to do that. And then they legally made it so you cannot do that. That's a Title IX violation. Yeah. Yeah. Also cannot ask you to come here and let everybody know I'm running late. Don't know why that's a Title IX violation. How the hell that one got abused. I also can't talk about what you got wrong in a class in front of other people. That's a FERPA violation. Anyways, so there's actually other forms of iron nitride, of course. So like if you had iron 2, right? Aluminum 2, the 2+ charge, that would be Fe3 in 2.
So if I ever saw an F2, I would automatically know it can't be anything in column 15 because none of those carry the 2 charge. It's got to be in the 16th column. Something had to be bonded to it because it's 2 and the 16 column is.
You mean this rubber dimmer?
Yes.
Yeah, 2+.
Well, if you had iron.
Let's look at that real quick. So rust, FeO.
Well, that you're affirming what I'm saying. If I see a 2.
Those are both rust.
If I see a 2, it could have been bonded to oxygen, sulfur, selenium. I don't know what Te is.
Oh,
anything.
I would not recommend trying to memorize those.
I'm not. I'm trying to make sure I understand. If I saw iron 2, that's going to tell me that that whatever it was bonded to, valence electron wanted to fill its shell with 2, so it's putting me in that column.
No, because again, like this one right here, this right here is iron 2, and that is oxygen with the 2- charge. But this one is also iron 2 right here.
Mm-hmm.
That one has the 3- charge.
Say that one more time, please.
This has a 3- charge here.
Well, then how did it balance?
These numbers. So this is 2 minus times 3, that equals 6.
Mm-hmm.
Okay. This one here is -3. This is times 2.
Yeah.
That equals 6.
Okay.
So
Okay.
that's actually why we're putting these numbers here.
Yeah.
Is because, like, you can have iron 3 bonded to anything over there. Doesn't
Right.
matter. Okay? It can take one electron. It could be fluorides,
Right.
in which case we have Fe. This is the 2, by the way. And that would be Fe2.
Right. Okay.
Okay.
It's kind of like they have to have a common denominator.
Exactly.
Yeah.
Yeah.
Got
And
it.
that's why we were talking about cross multiplication,
Right.
which is how you do common denominator.
Yeah.
Yeah.
Got it.
Did that fully?
Yep.
Yeah. I'll hold on to your marker again. I you know what? I'm just gonna. I need to give you a new marker at this point. That's what I really need to do. Dark blue. Okay. At this point, that's what I just need to do. All right. So again, remember anything that's in the transition metal area, and also the lanthanide series, which is that column below it, the periods below 6, 7 that are split out. They also do the same stuff. Okay. Anything that's in those, they have differential charges. They have different charges. Okay. Multiple charge states, you have to list what their charge is in their names because you won't know which one you're talking about. For example, you may have heard of like rust is iron oxide. It's actually more commonly the second one, but you do have some of the first one in rust. That's why they say just iron oxide and they don't give you any other information. It's a mixture. Okay, now polyatomic ions. Whenever we have a polyatomic ion present, remember that these are all together and they are a single ion. So phosphate is a single ion and it's a polyatomic ion, right? Okay. And remember, it has a 3- charge. Okay. So what we'll do is we'll just take that polyatomic ion. If we have to put a number next to it, we're going to put parentheses around it. And we're going to balance it as if it's one ion. Okay. And so you just do the exact same thing you did up here, but instead of it being a chlorine, a chloride, a fluoride, or whatever, it is a phosphate, a carbonate, a sulfate. Okay? Remember, they have to stay as one go, though. You can't split them up because they are one thing, right? So one of the common mistakes that happens, instead of this Ca3, see that Ca3PO4, and then we have parentheses, 2? That means we have 2 full PO4, right? One of the things people get tempted to do is they go Ca3PO. They do kind of 2 things, which are kind of weird stuff. I don't know why it's happening a lot, but that's not correct. Can everybody see how it's wrong? I added 2 to that. That's just not right at all, right? I've completely changed the identity. It's no longer a phosphate. Okay. The other thing you see a lot of is they'll go like this. Again, that's not phosphate, right? Okay. You gotta keep this is phosphate, and you have to multiply the whole thing, right? Is that making sense so far? Please don't fall into that rabbit hole. It'll like it's some sort of weird contamination that happens to people's heads, and then they have difficulty breaking that habit. Okay? So please be careful about that. You gotta take those polyatomic ions, they're one set. You have to modify the numbers of the whole thing. Okay, now nonmetals are going to combine by sharing valence electrons to achieve your octets. That's actually what you're seeing in polyatomic ions, by the way, is they are covalently bonding. They're nonmetals, and so they share the valence electrons. Ionic bonding, you just lose the electrons. Okay? So think of it like this. Ionic bonding would be like something that has very little strength trying to pull against something with a lot of strength. If I try to pull my arm with a pinky, what's going to happen? I'm going to lose, right? Okay. And so that's a metal trying to hold on to its electrons versus a non-metal. The non-metal just takes them, right? Okay. When you take two non-metals, it's like taking relatively equal strengths. And yeah, one might lose out a little, but it's not going to lose so badly it's going to lose the electrons. Okay? It's going to still maintain a connection to those electrons. And so that right there is covalent bonding. That's where you share the electrons to try to fill the valence shells. Okay? So you share the electrons so everybody has some. All right. The valence electrons in the bond, they'll belong to both of the atoms because both atoms are still associated with it. Okay? When atoms share, the result is a covalent compound. And so that's going to be what's referred to as a covalent compound. That is in versus an ionic compound, right? Which is what we had looked at before. Now, the smallest fundamental unit of a covalent compound is what we refer to as a molecule, and that's actually where molecules start coming in. Anybody know if they've ever seen a molecule with their eyes, by the way?
Well, if you've seen salt, you've seen a molecule.
Kind of, but that one's an ionic compound.
Oh.
So it's a little But your hair is actually a continuous molecule. So
Are your
each hair
nails?
strands. Kind of, but they wrap around on each other, and so it's a little weird. Yeah. If you look at an individual hair, it's a molecule. But yeah, your nails also, but unfortunately your nails actually have like cross-sectional molecules, and so it gets a little complicated. Okay, so naming the ionic compounds again, the number of covalent bonds that an atom will form is going to equal the number of electrons that's necessary to complete its octet. The use of electron dot symbols was actually first developed by a chemist. The name was G.N. Lewis. And so Lewis structures is what we're going to call these whenever we make these molecules using these structures. And it's going to tell you how electrons are actually shared in covalent bonds. Okay, what is sharing the electrons? How are they shared? Now, when you just write individual atoms, and you're trying to represent their valence shells, you're going to write out what's called electron dot symbols, okay? And it's going to be the elemental symbol, and then you're going to add dots for each valence electron around it. Okay. So here's the example, actually. This is a electron dot symbol for chlorine. And you've already seen these a few times, you just didn't know what to call them yet, okay? And so we put chlorine symbol, right, Cl, and then we add electrons around it. What you want to do is you actually want to add them one at a time and then eventually pair as you go around. Okay? And so you see here we have 3 pairs around the chlorine and then one by itself. Can everybody see that okay? Okay. And again, we look up at chlorine and what do you see? It has 7 valence electrons, doesn't it? So that's where that number 7 came from. That's that valence electrons around chlorine that we had discussed. It being one shy of an octet, right? Yeah. Okay, so what's going to happen here is when 2 chlorines come together, in fact, when you have a vessel with chlorine in it, this is always going to happen. The chlorines are actually going to each donate an electron into a bond. They're going to form a covalent bond between them. This is going to form what we call a bonding pair of electrons. So there are a pair of electrons that are involved in a bond. Okay? And this, we typically just refer to this as a bond. So this would be a single bond. We denote this single bond with a line like so. And that says, hey, these two are bonded together. Now again, what does that line actually refer to? It refers to a set of electrons that are being used in a bond, right? So that line is 2 electrons that are being shared. Okay? Okay. Now, you may have had a like high school chemistry, middle school chemistry, something like that, and you did bonding and you did Lewis structures. I'll give you my own method of writing these out. It'll be a little different than the book. My method's more complete, and you can never get anything wrong. Okay? I like methods you can do at 4 o'clock in the morning and be delirious and still get right. Right? Because I did all my studying at 4 o'clock in the morning.
I'm at work.
Well, I had to work night shifts. Yeah, so when my night shift cooled down.
Oh,
So whenever you write these out, though, I want to point something out. In my nice print, where I put these structures in print, these dots in the middle make perfect sense, right? And you can see them very nicely. Okay. I never ever want to see a student writing it like that. For you, from now on, every time you write it out, you will put a line for a bond. Don't put two dots in between. Because what's going to happen is you're going to get sloppy, and your dots are going to use pencils, right? And so you're going to go CL, CL, and you go. And then you're going to look back and go, this one's I think it's a dot in the paper, right? And so all of a sudden he comes back. Okay? And it may get so bad that you start doing that with pencils, right? So you have fine lead. And then you're like, those bonded? What? Was there a bond? I don't know what's going on. and it'll really get bad, okay? So when you need to make dots, you need to actually fill it, okay? And you're going to want to do that with your pencils and pens because a lot of them are just going to be too fine. Also, if you're using a digital tablet, oftentimes when you try to fill in, it will like open a menu. So what you can actually do is like that. If you use a digital tablet, okay? You'll see me do that sometimes when I'm using the tablet. Okay. Now this right here is actually a covalent compound. This is the diatomic, is what's called, because it has two atoms that are the same. And this has a covalent bond in the middle. This is a bonding pair of electrons. Again, it's a molecule of chlorine, gas actually. And this right here is a bonding pair covalent compound. Okay. Everybody good so far? Fantastic. This is actually a Lewis structure, by the way, right here. So we've actually made our first Lewis structure, okay? Yay. We accomplished one already. Okay, now this right here, electron dot structures, right? That's what these are. Okay. And this is what I never want to see you guys write out, right? It's always like that. Okay, so these right here are the electron dot structures for some various ones you're going to see a lot. So we're going to ignore the carbon for a little bit. We can actually see from our electron dot symbols that the nitrogen atoms can make 3 covalent bonds here. Oxygen can make 2 because it has 2 electrons it can share. Fluorine can make 1. Everybody see that pattern so far? Hydrogen can only make 1. It has 1 electron to share, right? Okay. And so carbon can make 4 bonds. That is true. Carbon can also do some fun stuff, right? Because it has 4 individual bonding pairs of electrons, right? So it can do some really fun and crazy stuff. Okay, so let's look at some other stuff. Now, single bonds. We could make 4 single bonds to complete carbon's octet, right? That would give it, each bond is 2 electrons. 4 times 2 is 8. Okay? Okay, now, carbon can also make what are called double bonds. A double bond is going to be denoted by 2 lines. And what it's saying is it's actually making 2 sets of electrons and sharing those with whatever it's sharing it with. Okay? For example, this could be another carbon over here. So these carbons on both sides would be sharing 4 total electrons in what's called a double bond. Okay? It is not the same thing as having 2 single bonds, but can everybody understand it forms double bonds? Those have 4 total electrons.
So you said if 2 carbons bind up, they'll make 2. So 1 pair and 1 pair, 2 double bonds, you said?
You can make a double bond between 2 carbons.
Okay.
It will make it every time.
Right.
Yeah.
That's.
Yeah, it can make.
But we don't, because we have single, double, triple, but we don't call it quad. We call it just 2 doubles.
2 doubles. Yeah. And so this one here is going to be 2 double bonds.
Mm-hmm.
And again, it's a very different sort of thing. So
So
having
will I see 4 lines between the carbons though?
no, that doesn't exist.
Oh, well, that's what I was asking you though.
And we can talk about it a little bit.
Okay.
So keep in mind again, 2 single bonds, very different thing than a double bond. Okay, you can have 2 double bonds. You can also have a triple bond and a single bond. Okay, now there is no quad bond. You know, it's not listed in there, and that has to do with the space around it.
Right.
So a single bond shares the electrons directly in between. A double bond actually is above and below, and a triple bond is in and out. Okay, so after a triple bond, you've actually filled up all the space between. You can't actually make a quad bond. That making sense so far? Yeah. Fantastic. Okay, so and again, we're shooting for complete octets every time. You will notice that I had skipped nitrogen before and didn't go into detail on that. Nitrogen can make double and triple bonds as well because it has 3 pairs of electrons, 3 sets of electrons it can make those bonds with, right? That can pair up. It can donate into bonds. And oxygen does have 2 single sets, and it can make 2 single bonds or a double bond. Okay. Notice the halogen group can only ever make 1 bond because it only has 1 free set of electrons, not already being used in a lone pair. Okay. Okay, that's the sulfur, by the way. It typically only makes 2 single bonds. It can make a double bond, but it's very unusual, and you'll probably never see it. Okay. Okay, so let's talk a bit more about molecular formulas. So for a covalent compound, this is going to identify all the components in a molecule. Okay. So the glucose is going to have a formula that's like so. We have C6H12O6. That was the glucose we had been talking about before. Okay. Notice that in this case, with these molecules, whenever we're talking about covalent compounds, right, molecular formulas, we do not divide by whatever can divide all the numbers. See that? If you were to write C1H2O1, that's a very different compound. Okay? That's actually one of the ketone bodies we had been talking about. And if you over have that, you can actually damage your liver.
Right.
Yeah.
Going to ask her if it's fabulous.
Yeah, it will be. Yeah. You got it. So again, this one right here is the glucose, C6H12O6, okay? If you have 6 carbons, 12 hydrogens, 6 oxygens, and they're in the same structure, that is glucose. If you doubled that, C12H24O12, that's actually what's called a disaccharide. It's a different sugar completely. Okay, totally different compound. Okay. Okay. Now, whenever we're looking at these, notice that these formulas do not show the structure at all. We have no idea, how are these carbons actually laid out, right? When we look at this formula, okay? So our electron dot symbols and our Lewis structures are going to help us figure that out. How are they sharing the electrons? How do they actually lay out, okay? And so this right here is going to be methane. So here you see actually the Lewis structure of methane. This is a more 3-dimensional space-filling model of it, okay? Okay, notice that this is all nonmetals, so it's a covalent compound. Again, the hydrogens each have to make 1 bond to the carbon. And so that's going to give us each hydrogen 1 bond, the 4 hydrogens around. Again, that is the Lewis structure right there. Okay, next time I'm going to start up on drawing out Lewis structures. If you want to kind of get ahead of it, I have a series of videos that take you through it on the YouTube channel. Okay? Yeah, actually, I had the note on my thing, and then I got stopped by 5 different people on the way to the markers, and I guess I forgot. I don't. I'm actually going to try to swing by there on my way here.
The Dollar General, the Dollar Store had it.
No, they have markers in the biology hall.
Oh.
Yeah, literally all I have to do is go to the biology